It's complicated.
All right, good morning.
Hi, Win.
Hi, how are you? I'm working on hydrocodone, so this is going to be fun. Vendors suck.
Yeah.
They all lie, and I don't know, I spend a lot of time at RSA and all around and go, how does your shit work? And, oh, it's magic.
Yeah.
Oh, thanks, cool, that really helps me. So for the last umpteen years, we've been working on a project to redefine security, and this is a homework session, which will mean that at the end of it, you're going to be given a homework assignment, and if you do the homework assignment and email it to me, it'll be your call as to whether I include it in my new book on this or not. You'll see where I'm going. This got advertised as a highly technical session, and it is, to a certain extent. We are going to be getting into a little bit of mathematics because wait a minute, you went to school, you're good, right? This is as complex as we're going to get. We're not going to get any more complex. Fundamentally, the top formula is what we've been working on and derives mathematically provable security. And I'll explain how all of that works and why it works. And it has been vetted. We've got full-time mathematicians working on it, and a little history. On the lower left, those establish trust factor and relationships between objects and subjects inside of any network. And when I use the word network, a network can be coding objects, it can be human objects, it can be network objects, it doesn't really matter. I'm going to be living in as an abstract a space as I possibly can.
Can we take a picture of that?
You can take a picture of anything you want at all. For anybody that wants the PDF after this, give me your business card and I will send you that, and then at the end it will be a crass commercial plug for you to buy my new book when it comes out soon. So the basics are these. This is what I have really learned over the last several years of poking around and getting deeply into the problem of why vendors are lying to us. And they are lying to us because they don't know any better and they care about quarterly profits, and they really don't give a shit about the performance of the technology, in my humble opinion. Everything you're going to see here is going to look like I might be introducing a product and a company. I sold my company. I am not building another company at all. I have no desire to productize any of what you're going to be seeing at all. I'd rather help the industry move along and get to the next step. The premise, the security models that we're using today in the real world are 45 years old. It's based upon asymmetric communications developed by Anderson back in '72 when ARPA, at that point, prior to DARPA, was trying to figure out how do we secure things. And some of you may remember mandatory access control, discretionary access control, A, B, C, D. And at the A level, there was mathematical formalism to be able to prove whether something was secure or not. We have not been able to do that since symmetric communications came along, notwithstanding any of the work by Shannon that was attempted to be thrown into this. So the goal here is we know shit ain't working, we need another thing to do. We tend to think that the world is binary, and it is really not binary. When we look at the fundamental error, perhaps the most, and I'm not sure I'm going to swear to that it's the most, but one of the most important failures that we have done over the last 40 years is we've accepted the concept of infinity in security. And that means, let's see, how long does it take to detect one of these APTs? What is it, 9 months? 12 months? How long has it been? It's 343 days was on one attack. And we're looking at these major attacks and we don't hear about them for a long time. The reason we don't hear from them a long time is because none of the current approaches to security are using an upper and lower time boundary conditions. They allow infinity to exist. And as long as you allow infinity to exist in any of your security applications, you're gonna fail, period, end of story. And we're gonna show you the math behind this to be able to prove it. So the thing that we need to do is start completely rethinking how we're viewing security. And again, these are object-subject relationships. You can look at them as a database relationship, but I tend to put that into another category. and I don't have time to get into that, but subject-object relationships at the coding level all the way up to the internetworking level. How are they communicating with each other, and how are we measuring that level of communication that's occurring, which then vis-a-vis says, how are we measuring the performance of vendor products that are claiming to provide security? And right now, we don't really have a very good way about doing it. However, one of the reasons is we're eliminating and have forgotten that the fundamental metric, the common metric between risk, privacy, and security has been ignored, and it's time. We do not use the time domain inside of any of our networking calculations, and I have sat with vendors at all the major shows, and as soon as I start talking this stuff, even the engineers start glazing over, and some of them will say, oh, we use a neural net, everything's good. No. Oh no, it's instantaneous. No, there is no such thing as instantaneity. We do it in real time. No, you don't. That's impossible. So the lies that are coming out of the vendors are prohibiting us from even having a benchmark on how bad or how good things may be. So part of the homework of this is going to be towards the end. I'm going to give you the techniques to actually measure quantitatively the performance of vendor networks, vendor products, and I want you to get back to me with the results, because we're only beginning this end of the project that is now going to be probably housed over in The Hague at a place called the Security Delta, which is a non-political international affiliation between business, government, and academia that doesn't have any of the traditional kind of DARPA bullshit and everything else. So we want to do the whole project over in Europe. We've been working with fortress mentality, which is the fundamental basis of the reference monitor and Anderson's work, which is great when you're in an asymmetrical communications environment. However, when you get into a symmetrical communications environment, the rules completely change. And they change to the point that they become almost unbelievably hard in order to do calculations. So the first thing we had to do was figure out what is the fundamental relationship between security and time. And the top formula there is the one that began it all back with a book I wrote called Time-Based Security in '98. And fundamentally it says, that top line, protection time. When you have a firewall, when you have a password control, any sort of security control at all, how long is it good for? How long can it sustain an attack? Regardless of whether the attack is exploiting a hole in the product or the service, or is it just good for that long as we might have with password cracking, and we're just doing brute force. How long does it take to do a brute force? We know how long that takes roughly. How long does it take to crack crypto? We have a reasonably good idea on various forms of crypto, regardless of how key management is done, as to, okay, this will be good for the age of the universe, or back in DES days, it'll be good for 24 hours, or in some MD5 earlier stuff, it'll be good for 22 minutes. It doesn't really matter. But we knew in certain cases how long the protection value of a certain type of encoding was actually working. And this was part of the design that was done mathematically. Now, in the physical world, let's say you're going to the office, and you go to the office and they have a nice alarm system. You got to open the door. What happens? The alarm gets triggered, and then you have 20 seconds, 30 seconds, some number of time to run over to the closet, open it up, and punch in the appropriate code so the goofy guys with guns don't show up at the door or call you or what have you. That is defined as protection time. And the reason we can say that in the physical world is because we have two other components that we can measure. The detection time. How long does it take that alarm system to detect that I've opened the door? Well, I don't know, 10 milliseconds, 2 seconds, I don't know, there's some number that's going to exist. The second number is RT, reaction time. How long does it take me to get from the door over to the alarm system and enter in a code that will deactivate the trigger? Those two sums are DT plus RT, detection time plus reaction time. And as long as they are less than the amount of time that I have in the protection circuit, I can then begin to say I have a provable amount of security for that specific example. However, in our world, PT, protection time, is indeterminate because there's no vendor on the face of the planet that will say, we guarantee our firewall will never be penetrated for 3 years. Any vendor promises, does anybody know of any vendors that will guarantee the amount of efficacy of their protective product? No, because they're not looking at the time domain, they're looking at your wallet. So we have to declare then that PT is indeterminate, in this particular case, sort of like divided by 0, and we end up with ET, exposure time, which says fundamentally, if I have no firewall, no protective circuit around a particular object that I'm trying to secure, the only security element that I actually have would be a proper detection reaction mechanism based upon the behavior of an external force upon the subject-object relationship. There is no other security necessary, and that gives us ET, which says that's my exposure time. That's the worst it could possibly be, which is creating what I call the upper time boundary of the circuit in this particular case, or of my protection, and I'm using protection in this case meaning ET, the exposure time, that'll be upper bounded by detection and reaction time. Everybody with this so far? Am I losing you? Are we good? All right. So the goal, of course, is really simple. We want DT and RT to approach 0, and that was that limit function you saw earlier. Simple calculus 101. I want DT and RT to approach 0, and that's a limit that will never be reached because 0 time, and I'm not going to go into quantum physics here at all. And that is the goal. Second thing that you have to keep in mind, especially when you're talking to your data people, look at the bottom formula. BW divided by IDBI equals 1 divided by the exposure time. And that has to do with the size of the database. In this case, we'll talk about an exfiltration perhaps, that the combination of the bandwidth of the circuits under analysis versus the exposure time tells us how much data could potentially be exfiltrated, assuming I did not have a decent detection reaction system in place, regardless of whether I had any protection, traditional vendor protection devices in at all. Are we good? Everybody good? Nodding, keeping notes, flashing pictures?
Can you say that one more time? BW and IDBI?
BW divided by IDBI equals 1 over ET, or you can invert the formula, of course. It depends how you prefer to look at it. It makes no difference.
And what's BW again?
Bandwidth.
Gotcha.
That's the bandwidth. That's the channel capacity if you want to play Shannon.
So basically, how,
Sorry?
given a time gap, given a certain length of time, how much data could be leaked during that period of time?
Data has a time component, and we forget that data has time built into it, not in stasis, but while it's in motion. And this has been another thing that we have ignored and forgotten about in security. Data has a time mechanism. Yes, sir? You got to shout it out because I'm deaf.
What is IDBI?
That is the size of an entire database under consideration. So, what we start talking about is the concept of feedback. Right now, everything that we do tends, I'm not going to say everything, the majority of what we do tends to be highly linear processing when it comes to production products, vendor products, network analysis, because everybody wants it to be done faster, 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 and there are fundamental mathematical limits of how fast things can actually occur if you want to have any security whatsoever. If you go outside those boundaries, which I'll show you how to do, then your security will by definition fail, and we've applied this to existing networks regardless of what technology they've got, and every single one of them architecturally fails and will never be able to be secure. So when we look at how the SCADA ICS world, anybody familiar with that? A little bit? All right, a little bit. When we did, hypothetically, the U.S. and Israel did the Stuxnet attack on the Iranian centrifuges, hypothetically. I don't care, I'm not doing politics here, I'm doing math. The attack was very simple. A centrifuge has a lower time limit and an upper bounded time limit based upon the mechanical constraints of the device itself. What happens if you remove the upper time limit boundary of it and let it approach infinity? What happens? What?
It burns up.
It burns up. It blows up. This is ICS SCADA 101. This is how jet engines work. This is how governors and steam engines work. It is through the concept of using feedback. And the feedback mechanisms that we know from the acoustic, electrical, and mechanical world have worked for over 2 centuries, yet in cyber, we have chosen to ignore it. So, we have the basics, and the only thing I'm doing over there is saying on the right, let's eliminate zeros and ones from all of our calculations. When somebody says, well, we're secure, bullshit. You know it and I know it, but I'm going to give you the math is to be able to prove it, that it is absolute bullshit. So, we live with SCADA-like feedback in our lives. Everything we do, from the thermometers at home, home automation stuff, it's all feedback-based in regards to sensors, which are detection, and reaction, which are the thermostats or the ball cock in your toilet. These are identical functions to what I'm proposing mathematically to do with network security. Now, the earlier talk was talking about neural networks and synaptic weighting. I'm not going to get too far into that, but the premises of what I'm talking about do have a large amount of ability to be migrated eventually, and we've not done this work yet, over to neural networks, because we're going to be coming, and I'll show you how this works, from a Bayesian approach. And largely, Bayesian applications are applied in many, many neural networks for reasons that are, well, they're completely counterintuitive. They make absolutely no sense until you get the answers, sort of like quantum mechanics. Anybody who claims they understand it doesn't understand it. It works. We can do the math on it, but we don't understand it. So the same thing is occurring with neural networks and feedback, and we have to start adapting how to apply these with time functions. Because even in this one, you don't see any time functions at all. But there are ways to do that, and unfortunately today I can't get into all of that bit. So our traditional networks, a lot of databases, a lot of servers, a whole shitload of connections going back and forth, but they're all highly linear when it comes to the transmission of the data and all communications. And there is very little out-of-band sensing, which is the detection and reaction going on at all. So I use this metaphor because it ends up being the fundamental of where the math is going to be going. There's 2 guys and they're walking in the woods, and suddenly there's the bear. And one of the guys starts running, the other guy sits down and starts taking off his shoes and putting on a pair of Nikes. The other guy says, "What the hell are you doing?" He says, you're not going to be able to outrun the bear." The guy says, "I don't give a shit about outrunning the bear. All I have to do is outrun you." And this is a fundamental concept that is part of SCADA and part of another thing that is called the OODA loop. Anybody hear of an OODA loop before? All right, I'm seeing a smile over there. Are you ex-military? How are you a little bit ex-military? What?
I said it's complicated.
It's complicated. He's a spy for North Korea. Get him out of here. The OODA loop was developed by John Boyd down at Montgomery Air Force Base and published in '84. And it was designed in order to be able to help fighter pilots optimize performance and survival in aerial dogfights. And it says fundamentally OODA. Observe what I got around me, which is detection. Orientation. Put it within a contextualized, meaningful place. Decide what are you going to do based upon the contextualization of the observation, and then take an action. Then do it again. Boyd's entire concept was the person in an aerial dogfight who gets inside of his adversary's OODA loop will be the winner. Very simple concept, and I don't think I have all the math up here in this presentation for it, but it is going to be coming out in the book about how all the OODA times tend to relate to each other. The thing that you've got to keep in mind with the OODA loop is that this is exactly how marketing and business is done. I'm going to sell green furry things because everybody wants green furry things. So I do some research and I collect my data. I observe, okay, everybody wants, then I contextualize it. Well, really only people in Wisconsin want green furry things. Now, I've decided to make Green Furry Things start marketing them, action, in Wisconsin. Then I'm going to begin looking at sales figures and doing market research and do the whole thing all over again. The tighter I make that loop, let's look at what Amazon does. They're magic in it. They have perfected the OODA loop, especially with their robot. You guys have all seen the robotic systems that they use up there and they put all the shit on the shelves completely randomized. It's not a stack of books and a stack of computers. They're random all over the place because they've optimized the OODA loop through the contextualization in the observation form of their own OODA loop in order to get that stuff into a cardboard box and out the door as fast as possible. Everybody with me on OODA loops? I know I'm moving fast. All right. Again, do we do any of this? We've done it in the physical world. We've not done it in the cyber world. And depending upon the complexity, you can play a lot of games, a lot of schematic games of how you want it to work. And what you're observing here is perhaps a little reminiscent of what you saw 3 slides ago, which was a neural network. There's a lot of weighting going on, but it always goes back to observations and contextualization. Otherwise, there is very little meaning in the data that is being collected. So in the real world, one of the greatest applications of OODA loops right now, have you guys ever seen like the 60 Minutes things of that poor lady who was a complete quadriplegic and now she can actually do things in the physical world with the brain implant? That is, right now, the neural implants are allowing OODA loops to operate at megacycles in order to give her machine and her body and her brain to be able to train each other vis-a-vis what we were talking, the guy was talking earlier with neural networks, by using these kind of feedback loops. Where are we doing this in information security, and why does information security still suck? Because the vendors suck. Any vendors in the room? Am I insulting anybody? Wait, that was a half a hand.
I don't really do the vendoring, but some of we have.
Yeah, but your hand is still up. All right, so you and the half military complicated guy can talk.
It's complicated.
Now, there are a couple cases that it actually works, and this is one that's using an out-of-band circuit, and I can't get into all the out-of-band reasons for things happening, but in this case, this is actually how my bank works. And I want to do something, and if I've not done it in a while, or I have my notifications and security set right, I want to move some money from one account to another, everything stops, which is the first step of the traditional Anderson reference model from '72. Then it goes over and uses an out-of-band communication channel, which Reference Monitor doesn't because they didn't need it in the asymmetric communication model. And it says, hey, Win, on a phone that has already a proven identity from earlier trust that was established, says, did you really mean, is this really you from your mobile or your laptop or wherever? Yeah, it's really me, and please do it, and then it goes ahead. So they're taking the Reference Monitor concept of a halt process, invoking an out-of-band process, but they're also invoking a time domain in there because that is good for what, 5 minutes, 10 minutes, depending upon the policy that is set by, in this case, it's Bank of America. They do the best security of any bank that I've seen thus far, at least in the U.S. And so this actually works very, very well using a time-based verification mechanism in the feedback loop. Okay? Got everybody? Any questions before I start making it harder? Okay. Now this is how my wife's car works. And this is maybe because we're a little older. In the old days, and that was like a year ago, when you want to make a turn, you do this, you do that, and if you're really a paranoid old fart like me, you may do it twice because some jerk's going to be coming at 120 down the road. My wife's got one of those newfangled cars that's got collision avoidance. Get it. Collision avoidance is there's a car, so you put it on your blinker and it says, whoa, beep, beep, no, and then that forces you, in theory, hopefully, to look. Is that a Volkswagen or is it a semi? I don't know. But if you don't get a notification, does that mean you should automatically change lanes? Are you putting 100% of your faith into a detection system that your particular Ford or Lexus or whatever it has? My argument, and my wife's argument is, because we grew up in the old school, no, let's verify what the CA is saying. Look thing, beep, ah, huh, huh. Now, if I waited 30 seconds for that, I'm going to be out of time bounds of validity of the verification due to the way the speed, the time it takes another vehicle to move perhaps within the CA system. Everybody got that? This is all about time. How long should that secondary verification take? And that's what's occurring in the decision time. In the feedback loop here, before an AND gate, and I will not change lanes until I have an affirmative in at least 2 ways on a single decision. And this is where we begin starting to see how we can apply these to our world and security. So, trust. Trust is not a binary function. I don't care if you believe your wife or your spouse or your friend will protect you at all times and everything. At one point or another, whether it's through torture or your children or somebody, we all have our breaking points. There is no such thing, I maintain, as 100% or value 1 trust. There is always some condition that trust can be broken. And over time, trust is broken. Trust is broken with networks talking to each other, because I trust Deloitte and Touche that their network connection to mine is really good, but do I believe that for infinity? That's the way we wire things now. We wire shit for infinity. Everything changes over time. You have an API and you're running a subroutine that's coming from an external, perhaps third-party vendor. How long do you choose to trust it? These questions are unanswered in our field. So let's take, in this case, the human issue. Somebody trying to get hired at a job, and in order to establish and make them a trusted employee, which is a misnomer in my opinion in many cases, what criteria are you caring about? So I carry the data over from the OODA loop, I contextualize it with the things that I care about. Then I can make a decision and act accordingly based upon that. But all of these criteria are going to change over time. So in a neural network, those would be weighted feedback loops that help go back and make the detection mechanism and the validation mechanism in order to get an output value of some sort more accurate with respect to this moment in time versus either 5 seconds ago, 5 days ago, a year ago, whatever that time period happens to be. And I don't have all the math here to show you because it gets really crazy, but we can be looking at logarithmic and exponential and somewhere in between linear fall-off rates of the way trust works. And we've actually been able to figure out the hard math on this, and that was part of that original crazy formula that I showed you. Now let's take this concept and put it into something that is called the two-man rule. Two-man rule came from banking, where Bob can sign for $100,000, but if it's 100,001, Alice has to sign as well. The two-man rule for verification. Perhaps you and your spouse have any check over $5. You both have to sign, depending upon how much you trust each other in that particular domain. So what we did is started looking at the world of Boole, George Boole from the 1820s, and looked at logic and found that it had a fundamental failing in that it was completely static. How do you turn Boolean digital logic into something that's analog? And what we started doing was putting time into the feedback loop to see what would happen. So again, in this case, Alice and Bob are a process, they're code, it doesn't matter, it could be humans. And in this case, we're using what is called a flip-flop. And a flip-flop, for those of you who grew up in analog electronics, anybody? Okay, all right, a couple gray hairs and a red hair. A flip-flop is a single bit of memory. Nothing more than that. However, we tend to use it as a storage mechanism versus a control mechanism. And we revisited this and said, what happens if we put a feedback loop in? So in this case, Alice is making a decision, whatever it happens to be in any of those domains. And in the output in this particular case, we're going to allow Q to go from 0 to high, go to 1, and enable whatever it was. So in this case, let's hypothesize that Alice is giving Sydney new access rights to stuff in the network. Cool. However, under the way we do it today, the amount of time that Sydney has access is infinite. There is no control mechanism. In this case, what we're saying is, all right, Alice trusts Bob with some number of trust, 0.9. I'm making a number up because it's easy to use the math. Now, let's say Bob has a trust value of 0.9 as well. Well, we'd like a verification of Alice's choice within a certain amount of time. The math works out, whether you're looking at a logarithmic or a linear, doesn't matter, decay curve, that we can actually measure the actual amount of trust over time that occurs for any particular action using this style of truth table, which is converting the digital Boole thoughts into an analog way of looking at Boole. And this is a fundamental component of where we're going to be going and how we start viewing networks using different kinds of building blocks. Policy down there is the time that we allow Bob to either validate or invalidate, or if he does nothing, then revocation of whatever Alice had chosen. And this can be done with a Q output or a Q prime output, or allowing Alice's choice not to be invoked until Bob approves within a specific amount of time. And that's just done through Boolean inverters, and there's no significant change in the logic. But this is the fundamental piece that we use. That's how it works. Yeah. All right. And I'm going to show you what this all means. And what those numbers are, the point up there in the sigma 1, 0.9 and 0.8, those are trust values. And again, they're very arbitrary to make an example here. And in this particular case, we've got 0.9 and 0.8. And in 0.9 and 0.8, we can do an arithmetic averaging and we get 0.85. Yet, however, if we start doing geometric averaging, we're looking for a different type of result. We're looking for greater, it's more of an indication that something is wrong. And using geometric averaging versus arithmetic averaging does this. So this is taking a Bayesian approach to the entire problem, which results in some very non-intuitive types of answers that come along. And I'm going to return to that once we add in the concept of, since protection is unavailable, let's invoke the concept of detection in depth versus defense in depth, because we know defense in depth doesn't work. We know that 91 approximate percent, assuming all the studies are reasonably accurate, of successful network attacks begin with out of bounds non-linear attack vectors. They occur through the human, which is an analog function. Yet the results of that become digital within our networks or the performance of code. So how many detection points do we have? Well, in a GE, I guess, I hope that's GE or it's Rolls-Royce, there are 5,000 detection points that are monitored and reported every single second. And now what does that do? Well, number one, it keeps optimizing performance and fuel and all that kind of good stuff going on. But what it also does is over learning and over time using neural networks, it helps us be able to predict failure in engines. That's why the engine reliability that we've seen today, barring that A380 engine that blew up a few weeks ago, happens. We know and tell by the way the 5,000 sensors are working. Some are strain gauges. Well, if metal starts stretching out of bands and out of bounds of the defined criteria, you got a clue something's going to go wrong. If you have thermosensors that are running around the engine and suddenly you have a 10% differential in a place that should only have 2% variance, you're out of behavioral bounds. And those behavioral bounds are determined by the engineering and design of the engine, which is nothing more than a mechanical network of components glued together in order to have an output, and that output is moved 50 tons through the air. So I've been looking at detection in depth as an answer to be able to apply some of this math to. And now this is where you guys are going to start coming in. When we look at detection circuits in the real world, it's at any kind, I don't care if it's antivirus, anti-malware, phishing detection. Makes no difference. How many of you have numbers from the vendor to say how long it will take that detection to occur with what level of efficacy? What's the confidence factor? Where's the mathematical proof? Now, you may hear, has anybody heard the term Six Sigma? All right. A lot of these vendors will say, well, we got Six Sigma performance. Well, let me run a number by it. Am I allowed to go over here?
You can do whatever you want.
I can do whatever I want. I'm going to break this table. Take a company of 10,000 people. We're going to say that there are 10,000 emails that come into that company every day, making up something, one per person, right? So what is that? That's 10 to the 8th emails. That's 2 orders of magnitude greater than Six Sigma performance by definition. So when vendors start telling you about Six Sigma performance, fuck them. It's meaningless when you are looking at the aggregate total in the OODA loop of the contextualization of the data across the entire problem. It changes your view completely when you start looking at the entire operation of a particular network or a piece of a network and starts throwing simple math at it. So in order to test any product, any of your IDSs, IPSs, AV, I don't care, this is your homework assignment. We all know what good traffic is, X. So on your test bed, just build an engine or get a vendor product and put it through, something's coming in, something's coming out, and make sure it's all good traffic. You can measure the input and the output and do a time vector on it, and that tells us what? The propagation delay of that particular circuit in that particular hardware environment and with the external BW versus IDBI input and output are. The numbers are there. How often have we ever measured? Has anybody ever measured this? Why not? You're from the military.
The military is really slow.
I can that.
So we don't even know what the propagation delay is given certain hardware specifications, even when they're talking about 4-core, 3.8 gigahertz boost power when there's a solar flare. I don't know what any of that shit means, but that's the way the vendors are talking. Now, so we have the propagation delay. That really doesn't matter what it is right now, but it's another measurement that you can't take. Now take a piece of known bad something, AV, IDS behavior, traffic, anything in the stack. Throw it into the mix, and you know that that black box should detect it. When you throw it into that mix, begin a clock. When the box detects it, hopefully it detects it, stop the clock. It's that simple. How long does it take? Everybody with me here? It's that simple. Throw in known bad traffic at the input. Begin a clock that'll start counting from 0. When it detects it, stop the clock, and you're going to have an answer that the vendor is not going to like, because we have already shown, not in really great laboratory conditions yet, 2 orders of magnitude difference in the performance of various vendors' products. 100 times better and or worse, depending upon how you're looking at it, of the performance of detection products in the network. I saw a hand over there.
Yeah, I worked for a company that did a inline IDS once, and it took more time for the good traffic to go through than bad, because they had to go through all the same.
Again, I
get the numbers, but I know what you're saying.
Yeah, and the limit function down in the lower left is simple Calc 101 or trig or algebra, whenever we all learned it. There is no magic here, and we can end up with a trust factor at the end of it based upon the data, which is back to BW versus IDBI, and we have more numbers. So this is the contextualization of the numbers with a single detection point. The GE engine does this at least 5,000 places every second. Networks, we suck. We're really, really
I
bad.
have two questions. One,
Yeah.
do we need to measure, like, kind of what he was getting at, I think, do we get any false positives that basically is what I'm asking?
Unfortunately, I don't have 8 hours to go through all that, or the curves, but there is, you know what a rock curve is?
No.
A rock curve is an XY matrix that basically has a set of data point samples that are called good and bad, and then just assume a linear line at 45 degrees. And anything above the line is good, anything below the line is bad. And depending upon if you're using Poisson distribution or Gaussian distribution or using natural distribution, you will start finding that the false positives, see, I gotta remember the formula here, this is Statistics 101. False positives plus true negatives equals the total number. And you can also invert that with true positives and false negatives. And it'll give you the sum. I'll give you a mathematical example of this. Let's say I've got 1,000 samples going in, and I get an output that says 11 of them are bad, but only one really is. What's the performance efficacy of my detection mechanism? The answer is 0.9%. So unless you're looking at false positives and false negatives and doing a Poisson or Gaussian distribution over the answers and applying some of the Bayesian stuff, you're going to get the wrong answer. So when a vendor tells you, well, we're 99.9% effective, so that means 0.1% of the time. Yeah, that's it, only 0.1%. Well, do the damn math. That's 1 out of 1,000. So if you have 1 out of 1,000, that is basically an unknown that requires additional verification to determine whether it's a false positive or a true positive. What does that mean to the performance of that particular box? It's for shit. And that's what we're dealing with these
Well, I'd
days.
rather hear that than I don't have any false positives, because that just means that they don't work.
Bullshit. No, there is no way.
Right.
Yeah.
I mean, if this is like so easy, then why don't companies?
Why didn't somebody else invent the wheel first? I don't know. I'm telling you, my research, I'm not defending it or any. We have seen no other work like this. We've shown it to the NSA, we've shown it to GCHQ, we've run it through the neural guys at Stanford, and the math works. Why nobody else is doing it, I don't know. Is somebody else maybe got bits of this in some of their engines? Maybe. I don't know. Well, how many security products are there? 3,000. I don't know one. I don't know any of them. I'm a theoretician. I don't give a shit. But I do care about how do we measure what's out there. And you guys can do this right now at home, and I'll give you the playbook on how to do it. Now, here's something that's really interesting. Let's just add one more tool here and say we got our clean traffic out, and we got another black box down there that we want to do the verification with. Is that a good thing or a bad thing? It is. It's a good thing.
Protection, yeah.
All right. I'm going to hold you to that. So we have 2 votes. It's a good thing.
I don't know.
I don't know is a really good answer for somebody in this class. And we're going to keep in mind that PT, protection, always has to be greater in time than DT plus RT, and that's why ET is our limit formula. Don't forget, limits are going to be at 0 and at 1. You're never, ever going to hit perfection. And any vendor that tells you that, they don't need both kneecaps for long. Now, one of the approaches to doing something like this, as an example, wouldn't it be great to get rid of phishing? All right, so what we got is user clicks on stupid shit. And right now, the user goes off at Geek clicks and something happens, and over on the side, there's a phishing detection mechanism that'll go, oh shit, you really should not have done that. What we're arguing is no. What I want to know first is the following. Here is my phishing box. Here is my fishing box. I want to know from the vendor, with known samples, how long does it take to detect it and react to it? And the reaction is, oh shit, this is bad. There is an amount of time that your guys are going to measure on all that stuff and send me the numbers. How do I solve the problem so fishing no longer becomes important? Over on the right, I've introduced the delay line. What is the value of that delay? Anybody, if you've been paying attention, you know the answer.
Detect time?
What?
Detect time?
Nope. What is the value of that delay line?
Less than protect time.
Less than protect time, but we don't know what the protect time is, do we?
Detect time plus react time.
Greater than detection time plus reaction time. Has to be, if it equals it, you can have error. My delay line has to be the sum of detection and reaction time plus some nominal amount of time after that. If it takes the fishing vendor 10 seconds to detect it, the user is going to notice and get really pissed off. If it takes 100 milliseconds, user's never going to see a thing. Now, part of the reaction that can go on in here is a message back to the user. That was really stupid, and it led down to this porn site, North Korean site, whatever. But the feedback mechanism not only should be with a go-no condition, it needs to be with a notification back to the user as part of the education, and developing an additional level of the database for more accuracy down the line. The thing that occurs here is when I have my trust factor built into this, and the trust factor is going to have to be, we'll just say 6 sigma at this point, so we're going to have 0.999999 effectiveness. We now have a provable metric of how good fishing is, the fishing detection is, and what would happen if I installed this inside of a big corporation? What happens to the likelihood of my fishing? The math shows it will decrease 10 to the minus sixth. Why aren't we doing it? I don't know. Not my job. I'm going to keep writing books and do research. Yes, sir.
Well, I suspect part of what you said about if it takes too long, the user will complain about it.
Then the vendors better up their damn game.
Yes, so you might have a site that is perfectly innocent for the first 10 seconds, and then it feeds up something delicious.
Agreed. However, whose job is that? Is that my job, or is that the black box detection job in order to keep its threat intelligence up to date? Whose job is it? Anybody?
NSA.
NSA's job, yes. It's the black box detection. When you hear about all these threat intelligence companies out there, they say, we have the latest and the greatest and all. Has anybody ever thrown time factors at it? Unless you throw the time domain into the equation, you cannot get an answer that's meaningful. It's impossible. All right, so that's one way and potentially on how to get phishing, and actually there's other circuits that we've designed that will also solve data exfiltration, which are, we call it the SMTP Ass Saver. It's a nice product name. And it does fundamentally the same thing with data exfiltration based upon a set of exfiltration rules that are done every day in IDS, IPS systems. However, they do them in line instead of introducing an appropriate delay based upon the performance and the efficacy of that particular detection system. Yes, sir?
One company I used to work for, anytime you sent a mail, there was a 1 minute delay before it actually went out, and every time you said, oops, I shouldn't have said that, cancel it before it actually went out.
Yeah, I mean, I think my Gmail, once in a while I see that it says, did you really mean to send this to all 7,000 people? No, I didn't, thanks. Same principle. However, mathematically bounded by measurable performance of the detection equipment is what our industry has not been doing. So we can do the same thing with measuring with 2 clocks. We can do the detection and reaction and parse them down to higher levels of granularity, especially when you're trying to design architectures to make this all work. The term that I've been using is called squeezing the loop. And I want that loop to get smaller and smaller and smaller and smaller, and I'm on an XY time axis, and I just want it small. And we have all the drawings in the math and shows what happens when they all fall out of bound. Now, 2 detection products. Here they are. A lot of people say, okay, I've got a good AV product here that I pay for from McAfee, and I got a free one over here that I get from wherever free stuff is. Is that a good thing or a bad thing? I heard 2 voices earlier, and I heard somebody honestly say, I have no fucking idea.
I was
What?
I was the one to say I don't.
So, what do we have here? We have 2 black box detection mechanisms operating in parallel, electrically speaking. Yes, sir.
A man with 2 clocks does not know what time it is.
A man with 2 clocks does not know what time it is unless the clocks are synchronized. That's absolutely true. That's why we have synchronized clocks.
That gives 2 attack points.
Okay, we have 2 attack points. All right, now this is where it's going to get counterintuitive. A lot of people think having 2 of these running in parallel, well, if A doesn't catch it,
In series.
then B will catch it. Mathematically, that becomes the OR gate at the bottom, and look what happens to the math. Suddenly, if I have 99% trust in each one of these, and I OR them together,
50.
it becomes down 98%. I've lost 1% in this particular case. However, if I put them in series, which is the AND gate, I'm increased in my efficacy by 2 orders of magnitude.
Defensive depth works.
Sorry?
So defensive depth works?
No, this is detection and depth. Detection and depth.
Sorry.
There is no such thing as defense. Well, there is defense. There's no protection. There is defense. This is counterintuitive. I don't expect you to get it right away. It just happens to be true. Any questions at this point up through Bayes and applying this concept into detection? Okay. So, again, the math here is still very, very simple when we're into the detection reaction. We're just adding more variables that are sitting around the clocks. The clocks are synchronized, but actually in this particular case, the clocks don't have to be synchronized, because when you're referring to a man having 2 clocks not knowing what time it is, that has to do with an absolute reference and not a relativistic reference. And in this case, we're doing relativistic references around each separate component. So it doesn't really matter. Okay?
I would also say no man knows what time it is.
Fine, we'll go with that. It's a relative 0. Can we live with a relative 0? All right. If we take the same approach, and I don't have the math here, again, I'm running out of time, I'm almost done. We can take this same approach and put detection mechanisms with measurable efficacy for DDoS attacks, beginning at the endpoint. By running out-of-band communications upstream throughout the various hops, I can share that data. If every hop has the same reaction process and detection process, what starts to happen if every single ISP on the planet participated? What would happen? Using that simple circuit, spam and DDoS go away. They die. The math is there, and it's using the same elements. You notice the 2 fundamental elements. Well, there's the clocking. We always have to be clocking to know what time element is going on, which helps establish the amount of delay that we need before traffic continues through to the next hop. And we have the time-based flip-flop down underneath of it, regulating the delay line based upon what is happening inside the detection and reaction modules at each particular point of your detection circuits. Engines, 5,000 of them. Cybersecurity today, 0.
But if they're all using the same logic, doesn't it ultimately they all also have the same capabilities?
Absolutely, and that's why you use an out-of-band command and control center And if you see down at the bottom, it's called the DRI, Detection, Reaction, Interface, and Reaction Matrix. And that is an out-of-band circuit that does not use TCP/IP, because TCP/IP has fundamental flaw that it has both the information and control signals running down the same wire, and when you get DOSed, you're hosed. You can't communicate on it. So you have to have an out-of-band communication mechanism the same way that I do with my bank when I want to move money. I've got to move my security communications off of TCP/IP and be able to measure the speed at which it all occurs. So what can you do right now? You can do this. All you have to do is go home and spend a few hours or go to work and get a lab on. You can measure this stuff right now. If you have more than one of them, compare them, see how they do. Put a McAfee versus a Semantic up next to each other on known AV samples. I'd love to know the answers, because we don't. This work in the formula is literally 7 days old. That's how recent it is, and we're finishing up and getting ready to publish. Let's see if we can get any data out of vendors. This will be a fun RSA for me coming up next year, especially once we have a few numbers.
And you have spoken to them, right? They usually can't even answer the basic questions.
Yeah, they can. The answer is, would you like a WebEx next Tuesday with that hamburger? So, your homework is going to be design a test bed, pick one of these things, pick one, and do these things, find the limits, and let us know the answers. We have not gone to formal test bed yet. We are trying to set up, as I mentioned, a lab over in Holland to be able to do this with no political or academic or vendor influence whatsoever. We want complete independence. And I'm giving you guys the first shot at, if you can do it, let us know what you find. Compare something and give us some data. Yes, sir?
If we do this and you use it, can we get a free copy of the book?
Yes.
Okay.
Yeah, absolutely. I'll even sign it for only $100. Yeah, if you bring us data, and yes, absolutely, if you bring us a good example, and spec out the hardware, spec out proper engineering specifications, because this is not a computer science problem. This is an engineering 101 problem. That's all that it is, and we have chosen to ignore it. There's the cover of the book. It's really a very pretty book. Very, very pretty. It's hugely pretty. Huge. We're back to my axioms, and then the book's coming out. We are doing the vetting and all of that. The math has been solidified and been approved by PhDs around the world. We honestly believe we do now have a mathematical model to do provable security. And we will be, this is the first time the formulas have ever been shown, and I'll be around. I know the next speakers want to get going, and I will be around for a little while if anybody wants to talk to me or try to call me out on my bullshit.
Doesn't the NSA hate competition?
Oh, thank you. Sorry?
The NSA hates competition, don't they?
The NSA, we've actually had a series of engineers and computer scientists go through to validate the math. And that's been done. I just got a text from one the other night that says, "You've really pissed us off." So this is the theory that we believe can, without restructuring TCP/IP at all, without touching it, we believe we know how to secure the internet. And any help that you guys can bring to the party with examples and testing, free copies of the book is the best I can do. But thank you for your time, and I'll be around for a little while. And do please call me out on my bullshit. I'm looking forward to it. Thank you.